One pretty common concept of the additional aspects to aqueous equilibria is the concept of an acid-base titration. A titration is a chemical process. It's actually a lab procedure where you're going to have a known concentration as well as a known amount of what's known as a titrant, and you will then be analyzing a known amount of what's called an analyte in an attempt to find an unknown concentration. This can happen with a process that's called redox, but this also happens with acids and bases, and it's most common with acids and bases. An example is outlined here. We've got a sample of hydrochloric acid, but we don't know what the concentration is. So what we're going to do is we're going to add, in this case, 0.45 molar sodium hydroxide to it. Now we know the exact volume of this, and what's going to happen is we're going to add this solution of sodium hydroxide until the pH reaches dead neutral. And what that tells me is I have exactly perfectly reacted moles of acid with moles of base. And if then I know the volume of each that I have used, I can go ahead and find the moles of base that I just put into that amount of acid, and that will allow me then to work back to find the molarity of that acid, because I obviously know the volume of the acid that I started with. I know how many moles of acid reacted with my moles of base. I can go ahead and do moles over volume and get my molarity of our hydrochloric acid down here. So there are special cases with titrations, and in this particular titration with a strong acid versus a strong base, the pH will be exactly 7 when we've reached a point where the moles of acid equal the moles of base. But as we continue through with these slides here, you want to pay attention to when that exact situation is going to not be the case, especially with weak acid, strong base, or strong acid, weak base scenarios. The setup you'd use in an acid-base titration looks pretty much like this. Your analyte will go in here, so this is our unknown concentration. It can be the acid or the base. We're going to use a piece of glassware that's known as a burette, and this is a really precise piece of volumetric glassware. And this is where we'll put our known concentration, and this will allow us to figure out, what amount we've added pretty precisely. We're going to know how much volume is placed into our Erlenmeyer flask down here. So at any rate, up here we have our titrant, what we are adding to the analyte. Now this is obviously a computer program here, but eventually what's going to happen is we're going to reach a pH of 7, and we can either have a pH meter reading the pH of this to tell us when we get to 7, or we can have an acid-base indicator. And that is what the next slide is going to talk about. Okay, so acid-base indicators, we have to know when we reach the point of a pH of 7, because that is when the titration is over. We don't want to add more titrant to the analyte, because that will obviously screw up our numbers, and we won't be able to correctly use numbers to find our unknown concentration. So there's a wide variety of indicators, as we can see here, and for strong acid, strong base indicators, we have a few that are particularly important to us. We want an indicator that changes pH right at 7. And the ones that we use are these three right here, or at least those seems like the ones that would be the most useful. But what we actually use most commonly is phenolphthalein. And now that changes pH a little bit above 8, and we want it to change pH at 7. So the explanation to why that's okay is going to come on the next slide. But what these are all liquid reagents that have a certain color when the pH is at a certain spot on the pH scale, and they will change colors when the pH changes. So obviously there's a lot of different transition points for these indicators, but if we're doing an acid-base titration, we want an indicator that tells us when we switch from acidic to basic, or specifically when we're neutral, because that's our indication of when to stop adding more titrant. Okay, so there's some terminology that we have to work through here and be comfortable with. The first thing is an endpoint. And what an endpoint is when our indicator changes color, plain and simple. Now, this does not tell us our equivalence point, which we'll talk about in a second. All this does is this tells us to stop adding titrant. The end point is when we change color. Now, very simply, the difference between endpoint and equivalence point can be made with phenolphthalein. Okay, we know that it changed pH or changed color at a pH of 8.4. Well, we know that the moles of acid equal the moles of base at a pH of 7. So the endpoint and the equivalence point can be different. Talked a lot about the equivalence point here so far. This is when the moles of titrant equals the moles of analyte. Plain and simple, this is when moles of acid equals moles of base. And in a strong acid, strong base titration, that will be right at a pH of 7. This is obviously going to change here in a bit when we get into the weak scenario, but I just want to make sure we understand that our equivalence point and our end point is not necessarily the same and often will not be. This is the most common indicator we use in acid-base titrations, and it changes color, or it lets us know that the end point is at a pH of 8.4, when really we had added we've gotten to the point where the same number of moles of acids and bases are in the container at a pH of 7. So as I talked about, ideally we would have an indicator that changes color at exactly the same time we reach the equivalence point. But that is not always possible, but that we can get around. Finally, a pH meter would obviously be our best bet at finding and stopping the titration at exactly the equivalence point, because once the pH meter reached a pH of 7, we would know that we have gotten to a point where we can end our titration. But a very important difference here between the end point and the equivalence point. End point being when we change color, equivalence point being when moles acid equals moles of base. Okay, so these things make a pretty distinct curve that we have to be familiar with to really talk in depth about titrations. So what this is this is a plot of pH versus milliliters of titrant added. So this is our pH versus milliliters of titrant added. So we can tell a few things about, first of all, what our titrant and what our analyte is. Since we start at a pH of around 1, we know that our analyte, what we start with in the Erlenmeyer flask, has to be our strong acid here. Okay, only strong acids have a pH of around 1. Since we finish up at a high pH, this is also a great indication that our titrant, what we're adding, is a base, because our pH is increasing as we add. All titration curves will have this general S shape, and they will have various rates of increase with this down here, but for the most part this S shape is going to be pretty standard with titration curves. Now, what I want to do with this curve is explain why phenolphthalein changing pH at 8.4 is not that big a deal. Here's 8.4 on the pH scale, somewhere right around there. Now, if we drop down, we notice that really we don't add all that much more base between 7 and 8.4 because of the shape of this titration curve. The pH changes so quickly when you get to the equivalence point that the end point and the equivalence point are essentially the same volume of base added. That's why it's not a big deal that phenolphthalein is what is used, and it changes pH at 8, or changes color, I'm sorry, at a pH of 8.4 as opposed to 7. Now, what I want you to get used to, this is a strong acid versus strong base titration. We start at a low pH, we finish at a high pH, and there's very little change in the slope of the graph until we reach the equivalence point, and then it quickly evens off just again. This is characteristic of a strong acid, strong base titration. Should we have titrated a strong base with a strong acid, the curve is just the opposite, like this right here. So that's what tells us what we're using. Okay, now this is the major points on the AP exam for titrations. I want you to notice how the shape of the graph doesn't change all that much, but where it starts is definitely a whole lot different. So if we look at where we start, now we start above 2. Remember, our strong started somewhere around 1. So there's a first indication that this is a weak acid that we're titrating with. Now, if we're titrating with a weak acid, we have to be reacting it with a strong base. And if we think about why that is, we can never react anything that is weak with another weak. So it is not possible here to react with a weak base. So if we identify that we're titrating with a weak acid because our pH is so high, we have to be reacting this then with a strong base. Okay, so a few questions to answer here. Why does the pH start higher? Well, weak acids are incapable of having a pH that is really below 2 even. So that's how we know that we start at a pH of, or I'm sorry, start with a weak acid here because the pH is above 2. Now, here we are at the equivalence point, and we're going to talk a little bit more in depth about this later, but for a strong acid, strong base titration, the equivalence point is at dead 7. And with a weak acid, it is not the case, and I'll explain more about why that is later. So that's pretty important here. Be listening for that coming up. Okay, so with our titration curve, we can tell a few different things. The first, a very important bit of information we can gain is the halfway to the equivalence point. Okay, so we are halfway to the equivalence point. That can tell us a lot about how our titration is going and when to think about stopping. So at the half equivalence point, I'll go ahead and address this now, the pH will equal the pKa of the acid. And that is because of our Henderson-Hasselbalch equation. Remember, pH equals pKa plus log of base over acid. Well, let's think about how this works. If we started with 1 mole of acid, weak acid that is, when we add a half a mole of base, what has then formed is each time we add some base, we are forming the conjugate base of the acid. And when we add a half a mole, okay, now halfway to the equivalence point, what we should have is a half a mole of weak acid and a half a mole of our base. So here's a half a mole of our conjugate base, half a mole of our acid. When we go ahead and divide this, because this is what goes right here, we will get the log of 1. And everyone knows the log of 1 is 0. So at halfway to the equivalence point, because each time we add a strong base to a weak acid, we're forming conjugate base. When we're halfway there, we have exactly the same amount of conjugate base and acid, and what that does for us then is result in a log of 1 in our Henderson-Hasselbalch equation, and we get the pH equaling the pKa. And we'll practice many problems where that is the case. Okay. Last different curve we see here, then we'll practice a little bit with these different solutions. We get here the titration of a polyprotic acid, and what you'll see here is multiple S's. You'll have as many S's as you do hydrogens. So if we move back here, if we look at this, here's our first equivalence point right here. Here's our second equivalence point, and if this continued, it would do something like this. So this is a triprotic acid because we have 3 different S's. There's 1, there's 2, and there's 3 right there. And really the only thing we need to realize with this is the characteristic shape of a polyprotic acid, multiple S's, and you can also then of course find the different Ka's or pKa's as a result of being halfway to the next equivalence point at each spot along the way. Okay, so what I have here is I want to work a few scenarios here. We've got a weak acid, strong base titration curve here, and what I'm working off of is your handout that I gave you that is your titration curve calculation worksheet in the packet from the other day, but you have to calculate the pH at 5 different spots. All right, so the pH initially is simply going to be the Ka of the weak acid divided by the initial concentration over x squared. So from that Friday quiz 2 Fridays back, that is essentially how you calculate the pH initially. Now, the second time where you're going to have to calculate the pH is when we get halfway to the equivalence point. And the trick for halfway to the equivalence point is what we talked about on the previous slide. The pH equals the pKa due to the log of 1. You have the same amount of acid and base at that point. Another spot where you're going to have to calculate this is at the equivalence point. So the pH at the equivalence point is solely dependent upon the conjugate base, because once you get to the equivalence point, all of your weak acid that's been reacted with strong base has been converted to water and weak acid. So this goes back to our talks on pH influencing ions. This is the only pH influencing ion now in the sample, and what that means then is this is going to slightly elevate the equivalence point pH of a strong acid and strong base and a weak acid titration. Notice how our equivalence point is above 7. It's because at the equivalence point, the only pH influencing ion, because this is an equimolar reaction. Okay, we put on the board equimolar reactions the other day between weak acids and strong bases and all the other different combinations. But at the equivalence point, the only thing left is the conjugate base of this weak acid, which is then going to slightly elevate the equivalence point pH of our titration. Now, before and after the halfway point, that's going to be our next one. I'm kind of running out of room here. Before and after the equivalence point, before and after equivalence point, this is a buffer. So what I want you to do is use Henderson-Hasselbalch. So all through here and all through here, that is a buffered solution, and you're going to use the Henderson-Hasselbalch equation to find the pH. The last situation where you have to find the pH is going to be after the equivalence point. And what this is simply at this point the pH depends solely on how much excess hydroxide that you're adding. So figure out how much hydroxide that you have added after the equivalence point, and you're just going to take the negative log of our hydroxide ion. And that's how that will work. I'm going to show you another curve, and this is the final slide here, and this is just a weak base strong acid. I want to show you that it's just the opposite of a weak acid strong base in that it starts up tall and finishes down low. And basically all the different calculations, the 5 that we did before, are the same 5 that you have to do here. And we will work on these in class, but it's good for you to see these now.